Next radionuclide presentation. Today, Titanium-44. As with all radionuclide presentation videos, today we talk a bit about the nuclear data, the gamma spectrum and other interesting stuff such as the application. First, a little unboxing, as this sample was gifted to us in this sealed container. Titanium-44, 3.7 megabecquerels as of February 7, 2008. This item had a contact dose rate of about 100 microsieverts an hour, which is why such videos are filmed behind a LED wall that shields most of our bodies. The hands aren't as protected, but they can handle a bit more exposure. There are even some special finger dosimeters, but exposure monitoring is a topic for another video. With a can opener and scissors, it's quick to be opened. A styrofoam holder works well to center the radionuclide in the vessel, ensuring the surface dose measurement is representative for this package. And of course there's a lead container, but it's far too thin for this level of activity. Here's a proper lead container with the appropriate wall thickness. And inside is the Titanium-44. This sample is in the form of titanium tetrachloride in this glass, which has turned brown from all of the radiation damage. A dose rate of about 1 millisievert an hour can be measured. At this point, I'd like to thank Radiacode for supporting this video. From now on, all the radionuclides where it makes sense will also be measured with the Radiacode. From the lead container, we measure 80 microsieverts an hour. Without the lead container, we max out the device with over 1 millisievert an hour and more than 50,000 counts per second. The good part is that due to this very high activity, within just a few seconds I could already record a complete spectrum, which we will examine later. If you want to have a 5% discount, use the link in the video description. Enough playing around with this hot sample, let's put it back in the lead container. Titanium-44 has a half-life of 59.1 years according to the Isotope browser. Its daughter nucleus is scandium-44, which is formed through the electron capture of titanium. Titanium does not undergo beta plus decay. Titanium-44 is produced using the isotopic target scandium-45, which is bombarded with protons. At proton energies of 20 to 30 mega electron volts, Titanium-44 can be produced via a P2N reaction. Titanium-44 has a specific activity of 5090 gigabecquerels per gram. But wait, if it's practically a pure X-ray emitter as a electron capture nuclide, why does the glass look so damaged? Let's examine the gamma spectrum. Okay, Titanium-44 is not just a pure X-ray emitter, it has also very low energy gammas. And a very dominant feature of the spectrum is the 511 kiloelectron volt line. This indicates beta plus decay from the daughter nucleus scandium-44. Scandium-44 has a 4-hour half-life, about 2.5 mega electron volt positrons, and additionally emits 1157 kiloelectron volt gammas. Yikes. This explains the absurdly high dose rate that we measured and the radiation damage on the glass. And there's also a sun peak caused by the very high activity of this sample. Now onto the application. Titanium-44 is used in a scandium-44 generator system for nuclear medicine. Titanium has a half-life of around 60 years and decays into scandium-44 with a 4-hour half-life. After about 1 day, the system reaches circular equilibrium. So the generator exploits titanium for its scandium production. Scandium-44 is the star of the show. Titanium is loaded onto an ion exchange column, where it sticks and produces scandium-44. The scandium 3+ ions are complex with oxalic acid and eluted using hydrochloric acid. By the next day, the generator has produced sufficient amount of scandium-44 again to be milked again. The scandium is further purified by freeing the oxalic acid with a cation exchanger and then eluting it with a ammonium acetate buffer. But why do we need scandium-44 in nuclear medicine? It's used as a PET tracer in PET-CT scans. PET here refers to positron emission tomography, not the plastic used in water bottles. Scandium-44 is a positron emitter. In PET scans, the positron emitter binds to target location in the body based on the chemical packaging. It then emits positrons which annihilate with the nearby electrons, and this annihilation releases two 511 kiloelectron volt photons in almost exact opposite directions. By detecting these photons at either end of the patient, the location of the annihilation and hence the radionuclide can be traced back. However, the exact location of the annihilation differs slightly from the radionuclide itself due to the positron's travel distance, which depends on its energy. Low beta plus energies reduce this uncertainty, but scandium-44 unfortunately has a relatively high beta plus energy. The advantage of Scandium-44 hereby is its 4-hour half-life, which allows for longer imaging periods compared to shorter-lived positron emitters, which can be advantageous in some cases. Moreover, Scandium-44 decays into stable and harmless Calcium-44. Typically, PET imaging is combined with CT scans to produce better images, as PET scans alone aren't used anymore. Coming back to the chemical packaging of Scandium-44. Scandium-44 is unique among PET nuclides because it's a metal ion. Other PET nuclides such as carbon-11, oxygen-15 and fluorine-18 form covalent bonds. Scandium-44, on the other hand, must be chemically packaged as a complex, often with a ligand called DOTA, 1,4,7,10 tetraaza-cyclododecan 1,4,7,10 tetraacetic acid. Let's stick to DOTA. DOTA wraps around the Scandium-44 and is then conjugated to a peptide for selectivity. In one study, Scandium-44 wasn't produced via titanium generator system, but instead through proton irradiation of Calcium-44. This Scandium-44 was then conjugated to a dimeric cyclic RGD peptide using DOTA. RGD stands for arganyl glycyl aspartic acid. The dimeric form creates a ring structure incorporating tyrosine and lysine to provide specificity for the alpha-v-beta-3. It's a type of transmembrane protein. One function of this protein is that it lets cells stick together, and the overexpression of such proteins is linked to tumor aggressiveness. So with this CRGD cyclic peptide, you can track down a overproduction of this protein, and with that, the linked Scandium-44 will then stick to the tumor and can be measured. That was a lot of information. Thanks for following along, and with that being said, thank you for your attention and goodbye. A special thanks goes to the Working Group of Analytics and Fundamental Nuclear Chemistry from Dr. Erik Strupp and the Division of Nuclear Chemistry at the University of Cologne, and to my Patreons. 14710 tetraaza cyclododecan 14710 tetraaza cyclododecan cyclododecan 14710 tetraaza cyclododecan 14. Why is it English so hard? 14710 tetraaza cyclododecan 14710 tetraacetic acid.